Hi, I'm Rodolphe Lepigre, and on behalf of my co-authors, I'm going to present VIP, which is a step towards the verification of real-world System C code. There are loads of challenges, so we focus on just one, which is to support code involving integer pointer casts, since System C code relies on them, and they have particularly tricky semantics. An example of use of integer pointer casts is pointer tagging, which consists in writing metadata in otherwise unused bits of pointers. And here is what a typical tagging function looks like. It takes as argument a pointer p that may already have a tag and a new tag value t to apply to it. The function then starts by casting p into an integer I, and then the tag is written using integer arithmetic, and the result is stored in variable new I. And finally, new I is cast into the result pointer q. So what we've seen here is that the tag function relies on the fact that pointers are not just abstract values, but also have an integer representation that can be manipulated. Hence, in order to verify such code, we first need to answer a big question. What is the semantics of pointers and integer pointer casts? Although this question may sound simple, the design of a memory object model is an active research area. The main reason why integer pointer casts are complicated is that there is a tension between a concrete and an abstract view of pointers. In a fully concrete model, where pointers are represented as simple integers, integer pointer casts are trivial identity functions. However, such a model is not sound with many optimizations performed by compilers like GCC or Clang. Dually, in a completely abstract model, where pointers are abstract entities, many standard optimizations are justified, but code like our pointer tagging function is not supported. So, in a way, the concrete model is too concrete, the abstract model is too abstract, and what we want is something in the middle that is just right. And that's what we've called a Goldilocks memory model. In fact, there has already been quite a bit of previous work on the design of such Goldilocks models, and amongst them is PNVI AEUDI, or PNVI for short, and that is the model upon which our work is built. So, you might wonder, if PNVI is already one of these nice Goldilocks models, why not just take the paper where it is described, implement it in a program verification framework, and get done with it? After all, PNVI is a pretty good model. It has been substantially validated against not only the C standard, but also de facto practices when they happen to diverge from it. It is also mostly compatible with the optimizations performed by compilers like GCC or Clang, and it might even become part of the C standard in the future, or at least is currently the preferred option. The downside of PNVI is that in order to do all these good things, it needs to just work with a lot of existing C code, and as a consequence, the model is very complex. For instance, PNVI has to deal with integer-to-pointer casts for pointers whose address points both at the start of an allocation and one past the end of another. And it does so by tracking both possible provenances at once until a choice becomes necessary. So overall, PNVI is not directly suitable for verification, or at least it is unappealing due to its complexity. However, since there are loads of good things about PNVI, what we ask ourselves is, how can we build a verification framework atop PNVI anyway? So what we've done in this work is design a new memory object model called VIP, which is targeted at verification. And in particular, it is much simpler than PNVI. To demonstrate that VIP is suitable for verification, we have extended the refined C verification framework to use VIP, and we verified a number of integer pointer cast idioms using it. Moreover, what is great about VIP is that it is compatible with PNVI, in the sense that whenever a program has undefined behavior under PNVI, it also does under VIP. As a consequence, we proved a theorem stating that when a program has been verified under our version of refined C based on VIP, it does not exhibit undefined behavior when executed under PNVI. What this means at a higher level is that, at least as far as the memory object model is concerned, a program that has been verified with refined C can be compiled with GCC or Clang with some guarantee that it will not go wrong. Now, let me quickly explain the key idea of VIP, which is to require the programmer to annotate integer-to-pointer casts with a provenance. Intuitively, a pointer's provenance identifies a corresponding allocation, and in both PNVI and VIP, pointer provenance is what enforces that the model is abstract enough to support compiler optimizations. Going back to our pointer tagging function, we can make two observations. First, the argument pointer p comes with a provenance, but provenance is not propagated via integer arithmetic. And second, when new I is cast into a pointer q, a provenance needs to be constructed for it. Clearly, tagging a function should preserve its provenance, so q should be given the same provenance as p. However, this is not at all obvious to PNVI, and in some cases it may need to work with an ambiguous provenance. To avoid all ambiguities, VIP requires replacing the bare integer-to-pointer cast with the use of a specific copy allocatee instruction. and this instruction performs the cast, but additionally assigns the provenance of its second argument to the obtained pointer. And thanks to this idea, VIP can be easily integrated into a verification framework like refineC that can then be used to verify functions like tag. Now that you have a general idea of the approach, let us take a closer look at the details, starting with the semantics of pointers in VIP and PNVI. Remember, since these models are Goldilocks models, they need to strike a good balance between abstraction and concreteness, so as to both support compiler optimizations and integer pointer casts. And pointers are thus represented as a pair of a provenance and an address. On the one hand, the address makes pointers concrete and gives them an integer representation. And on the other hand, the provenance introduces some abstraction by restricting how pointers can be used. In particular, a pointer is only valid for accesses if its address is in the footprint of the allocation identified by its provenance. And the only way to create a provenance is via allocation, which assigns a fresh provenance to the resulting pointer. And this provenance is then preserved by pointer arithmetic as long as it remains within the bounds of the allocation. However, importantly, there is no general way to create a provenance out of thin air, which is to say that one cannot create a usable pointer out of thin air. And that's a very good thing, because if the model allowed that, then it would invalidate many interesting optimizations, exactly like in a fully concrete model. Okay, so now that we know how pointers are represented, let's see how integer pointer casts are defined. We're going to look at both directions, but let's start with the easy one, which is pointer to integer casts, here shown on the left. So if we want to cast some pointer with provenance p into an integer, what we do is that we simply forget about the provenance and just keep the concrete address. And that is roughly what happens in VIP and PNVI. Now, let's look at the more interesting case, integer to pointer casts, shown on the right. If we want to cast some integer into a pointer, what we need to do is produce both a provenance and an address. For the address part, this is easy. We simply use the integer as address. However, the question is now, what provenance should we use? And that is where things start to get complicated, especially in PNVI. So, how does PNVI build a suitable provenance in the case of our example? The answer is that it needs to inspect the heap, or more precisely, certain metadata related to allocations. And these allocations are shown here using a red square to identify their footprint, and the corresponding allocation identifiers appear on the far right. And in fact, the only allocations that we care about and represent here are those that have not yet been deallocated, and that have additionally been marked as exposed. And an allocation is exposed when its provenance has been leaked, which typically happens when a pointer with that provenance is cast into an integer. But in simpler terms, the allocations shown here are those who could potentially be used as provenance when casting an integer into a pointer. Now, going back to the pointer we were creating in our example, we can see that its address points somewhere in the middle of allocation 7. And so this is a relatively simple case. Since 7 is the only suitable provenance, 7 is picked. Now, if the address does not lie in the footprint of any live and exposed allocation, then the situation is similarly simple. Since there are no suitable provenance, an empty provenance is used and the resulting pointer is not valid for accesses. However, there is a third kind of situation that may arise, and that is the source of much of the complicated nature of PNVI. What if our address points at the start of an allocation that is immediately preceded by another, both allocations being alive and exposed? In that case, just picking 7 is not right. Indeed, it is not the only choice due to the fact that in C, a pointer to an allocation is also allowed to point 1 past its end, and hence 3 would also be a possible choice here. So since there is no way to tell what the right choice is, PNVI relies on the symbolic provenance S and avoids to make a choice until it becomes necessary. And this typically happens when a pointer with provenance S is used for a memory access, in which case both options cannot be valid at once since the two allocations are disjoint. Okay, enough of PNVI. Let's see what VIP does when presented with the same situation. And this may sound a bit disappointing, but VIP never tries to be smart and just picks the empty provenance, which yields a useless pointer. And it does that even in cases where there is no ambiguity. But remember, integer to pointer casts are not the way in VIP. As we saw earlier, the key idea of VIP is precisely to replace integer to pointer casts with a specific copy allocating instruction. And this instruction lets us pick the provenance of the result using an argument pointer from which the provenance is copied. And so instead of ending up with a pointer with an ambiguous provenance that could be either 3 or 7, we instead obtain a pointer with exactly the provenance we want, in that case 7. And contrary to the pointer obtained using the cast on the left, the pointer obtained via copyallocad is valid and can be used for accesses. Now, since programs running under VIP rely on the copyallocad instruction, you might wonder, how can we interpret these programs under PNVI since PNVI does not have the instruction? In fact, the statement of our main theorem, which I showed earlier, was incomplete, since it ignored the fact that VIP programs do rely on copyallocad. And it should really say something about the implementation of copyallocad under PNVI. But what should its implementation look like? Well, the main role of copyallocad is to perform an integer to pointer cast, so it should look somewhat like this. And you can see that this function indeed returns the result of the expected cast, which does not at all involve the pointer from which the provenance is meant to be copied. However, there is a problem with this implementation, and it arises when the from pointer has a provenance that has not been exposed in the PNVI sense, meaning that under PNVI, this provenance cannot be used on an integer to pointer cast. What this means is that there are programs for which copyallocad returns a valid pointer in VIP, but a pointer with an empty provenance under PNVI. And that's bad, since our theorem relies on the fact that VIP has more UB than PNVI. And that lemma is simply false with the implementation I'm currently showing. However, that can easily be fixed. The solution is simply to ensure that the provenance of from is exposed prior to performing the integer to pointer cast. And all we have to do for that is insert a dummy pointer to integer cast, whose result is never used. And this dummy cast is of course not just for show. It actually influences the optimizations that compilers like GCC or Clang will perform. To evaluate the impact of replacing casts by copyallocad on the performance of the generated optimized assembly, we relied on a pre-existing test suite which was specifically designed to exercise the behavior of PNVI on integer pointer casts. Among the 44 programs we considered, a third have undefined behavior under PNVI, and so it does not make sense to generate assembly code from them. Then, another small third of the programs are well-defined under PNVI, but do not require any modification to also be well-defined under VIP. And what that means is that we can just use the same program under both models, and hence the performance of the generated assembly is obviously the same. The most interesting group of programs is the next one, which also contains about a third of them. These programs are well defined under PNVI, but they need to be modified to not have undefined behavior under VIP. And that just means inserting copyallocad here and there. For each of these programs in the green group, we compiled the original code as well as the modified version using GCC, and we obtained the exact same optimized x86 assembly code. So there is no difference in performance between the two versions. We also ran the same experiment with Clang and got the same result except for one example. However, the difference is small. It only concerns the setup of a call to printf, and the instruction count is the same anyway. Now, you may have noticed that two programs are not accounted for, and it turns out that these two programs are well defined under PNVI, but cannot be made to not have undefined behavior under VIP. And this points out to one of the limitations of this work, which is that to use copyallocad, you need to have a pointer with the right provenance on hand. That seems to be the case most of the time for practical examples, but there are programs like those in the red region for which this is not true. Using the same test suite as in the previous slide, we also empirically validated our main result. That is, the lemma saying that VIP has more undefined behaviors than PNVI, but that when a program has defined behavior under both models, then the behavior is the same on both sides. To do that, we extended the Cerberus C semantics with VIP, and since Cerberus already contained an implementation of PNVI, we relied on it to check whether the examples have undefined behavior under either model, and if the behaviors indeed match when they are both defined. For each program, we tested both its original and modified version under the two memory models, and I'll now describe the 5 different outcomes that we have observed on the 44 examples of our test suite. First, 12 programs are deemed defined by both models and have the same behavior, and for these we do not need to modify the program in any way to run under VIP. Then 13 programs have undefined behavior under both PNVI and VIP, independently of whether we replace casts by uses of copyallocad. Then there are also 2 programs that similarly have undefined behavior under both models, but their annotated versions are both defined and have the same behavior. Note that adding copyallocad can eliminate undefined behavior also on the PNVI side, due to the fact that it forces the exposure of the provenance of its second argument. The next line gathers 15 programs that have been defined under PNVI, but that have undefined behavior under VIP. And their modified version is defined under both models and have the same behavior. And finally, the last line is for the two programs from the red region of the last slide. They are defined in PNVI, but they cannot be made to not have UB under VIP. Now, for our soundness result, what is important is not to have a program that, at the same time, has undefined behavior under PNVI, but is defined under VIP. And there is indeed no such program here. You can see that in the two lines where the original program has undefined behavior under PNVI, it also does under VIP. And similarly for the line where the modified program has undefined behavior under PNVI. However, it is perfectly fine to have a program that has undefined behavior in VIP and that is defined in PNVI. In other words, VIP can have more undefined behavior than PNVI. Okay, so in this talk, I have mostly been talking about the memory object model side of VIP and not very much about program verification. But an important part of this work has actually been to extend the RefineC verification framework to support VIP and to use it to verify programs relying on integer pointer casts. To show that the obtained system is suitable, we have conducted 4 case studies. We wrote the code for the first 2 ourselves, but they are meant to exercise 2 standard manipulations of the integer representation of pointers. The first one is a pointer tagging library, a function from which you have already seen. And the second is about using the underlying bytes of pointers to store unboxed integer values, as is often done in languages runtimes, for example, in the OCaml runtime. The next 2 case studies consist in verifying real-world system C code, a simple page allocator from the PKVM hypervisor, and a lock ordering function from the spinlock library of the Hafnium hypervisor. To give you a feel of what it means to verify code involving integer pointer cast in RefineC, I'm going to conclude this talk by taking you through the process of verifying the tagging function from earlier. What we need to do for this is first give the function a specification using special RefineC attributes, and I'll take you through these in a second. And we also need to additionally give another attribute with some cocktactic to help RefineC's poor bitwise arithmetic automation through the verification of this bit of code. Of course, that could go away with a bit more engineering work. But now, with these annotations in place, RefineC can verify this code fully automatically with no further input. Now, let's look at the spec in details. As you can see, there are 4 kinds of RefineC annotations here. There are parameters which declare variables that are universally quantified in the spec, together with their type. Here, R is a pair of a location and an integer, T is another integer, and Ty is a RefineC type used to make the spec polymorphic. Then the args annotation gives RefineC types to the arguments of the function. So the first argument is specified to be a tagged pointer, and that makes sense since the function can be used for retagging, and a suitably aligned pointer can always be seen as a tagged pointer with tag value 0. The second argument is given the type of an unsigned 8-bit integer, as expected from the C type. Note that RefineC uses refinement types with the @ notation. Here, our integer argument is refined by t, which constrains our parameter t to be equal to the tag value specified in the argument. The next annotation contains 2 preconditions. The first one constrains the tag value given as second argument so that it is a representable tag value. The second precondition is a bit technical, but it constrains the type of the memory pointed to by our tagged pointers. And finally, the last annotation specifies the RefineC return type of the function. It should be a tagged pointer to memory of the same type as the argument pointer. What changes between the type of the first argument and the type of the return value is the refinement. As you might have noticed, our tagged pointer type is refined by a pair giving both the memory location that the represented untagged pointer points to and the tag value stored in its representation. And so you can see that in the return type, the tag value has been changed to t, but the location is the same as in the argument, so the old tag value was replaced. And that's it for the spec. With that, I'm done with my talk. Thank you very much for your attention. And if you want to know more about VIP, please have a look at the paper. It contains a few things I did not have time to present, like our special handling of round-trip casts.